Hi, my name is Zhong Chen, a PI in Neuroscience Institute in our Zhejiang University. One of my research interests is epilepsy. In my lab, by using the Optogenetics multiple channel EEG analysis, imaging, electrophysiological and molecular techniques, we are trying to explore the neural mechanism underlying the generalization of seizure in epilepsy. Our goal is to look for a novel therapeutic approach for epilepsy treatment. Recently, one of our works has been published in Neuronal, which was finished by Dr. Wang and Dr. Xu. In this study, we aim to review the neural mechanisms in the subiculum, especially the function of the intrinsic microcircuit in secondary generalized seizure of temporal lobe epilepsy.
Cooperated with Epilepsy Center in Second Affiliated Hospital, Zhejiang University, we performed 3D MRI imaging in temporal lobe epilepsy. We found that epilepsy patients had significantly smaller volume of all hippocampal subregions compared with healthy people. However, only the subiculum showed an additional reduced volume in the presence of secondary generalized seizures. Next, we move on our work to a mice kindling model in which we implanted electrodes into the hippocampus and then delivered electrical stimulations to elicit seizures with different scores. First, we used VGAT-CHR2 transgenic mice for selective activation of subicular GABAergic neurons with a fiber placed above the subiculum. Single-unit recording showed that the blue light photostimulation reliably enhanced the firing rate in GABAergic neurons, and majority of putative pyramidal neurons were inhibited by photostimulation through GABA-A receptor. In kindling model, photostimulation retarded the development of behavioral seizure stage and shortened after discharge duration during generalized seizure acquisition. Interestingly, when mice were fully kindled, photoactivation of subicular GABAergic neurons even activated a large proportion of pyramidal neurons and prolonged after discharge duration and generalized seizure duration. GABA-A receptor channels are mainly permeable to chloride. Grammy-seeding perforated patch recordings show that the GABA-A receptor-mediated currents was much more positive in subicular pyramidal neurons from mice that had experienced generalized seizure expression. This situation was caused by the changed expression of chloride cotransporter NKCC1 and KCC2. If we apply the selective NKCC1 inhibitor bumetanide or shRNA to selectively knock down the expression of subicular NKCC1 in kindled state, and photostimulation restored the anti-epileptic effect on SGS expression. Then, to mimic the inhibitory effect on pyramidal neurons when GABAergic neurons were activated, we optogenetically inhibit pyramidal neurons with ARC, a proton pump, or NPHR, a chloride pump. Photostimulation of subicular pyramidal neurons targeted with the ARC, but not NPHR, mitigated the severity of SGS expression, verifying an imbalance of chloride homeostasis in pyramidal neurons. Finally, as there are mainly two subtypes of GABAergic neurons in the subiculum, pavbooming expressing neurons or somatostatin expressing neurons, we found that PV or SST interneurons are differently involved in SGS expression. Photoactivation of subicular PV neurons aggravated the GS expression, while photoactivation of subicular SST neurons effectively alleviated SGS expression, suggesting that subicular pavbooming but not somatostatin subtype GABAergic neurons are easily depolarized in SGS expression. In the present study, we first reported in vivo that the subiculum may serve as the choke point for controlling of synchronous firing spreading from the hippocampus during generalized seizures, and the depolarized microcircuit activity caused by the change of chloride transporters mediate GS. This may be important for the design of site-specific therapeutic interventions.